Hello, today we will discuss about uncertainty principle. The Heisenberg Uncertainty Principle is based on the wave-particle duality of matter or quantum particles. The principle states that two quantum mechanical variables or two canonically conjugate quantities, they cannot be measured exactly simultaneously. So the measurement simultaneously, it's quite not possible in the quantum mechanical realm. Now what is the meaning of this thing? Now when you think about a quantum mechanical particle, we need to think about some wave packet or a matter wave. So what is this matter wave? So this matter wave concept was given as the concept of phase velocity and group velocity. So the phase velocity when the individual waves are moving, individual harmonic waves are moving. But as a group, when the number of harmonic waves are in a superposed form, they are moved in form of a group. So the velocity of this group is known as the group velocity, Vg. Now obviously when they are superposing, you will get a certain region, something like this. So the matter wave or the wave packet can be represented by this type of form. Now this particular region where you have the probability of finding the particle. So we are talking about electron or electron-like particle. So you will have a certain zone, you have a certain region where you can get the particle. Normally in classical world what happens, we need to define the position. Say if you are talking about a certain position somewhere here, this may be represented as x, y and z, or in one dimension this is x. So you can definitely say that the position of the particle is x. But what happens in case of quantum mechanical world, this is the region where the particle will be available. Now to explain this thing, we will going to use one simple experimental idea which is known as the gamma ray microscope experiment. In this experiment, what we are assuming that the electrons are available, so it's represented by a circle, but actually it is represented by this wave packet. Now what happens when to see any object, we need to put some light, put some photon over there. So when photon falls, this will be absorb some amount of photon energy, so there will be scattered photon in a particular direction and recoil electron in any other direction. So this is the case of a Compton effect. Now as the dimension of the particle or the mass of the particle, the electrons, this is very very small, so obviously there is a chances of scattering of photon and recoil of electron. The scattered photon will be captured by the microscope, so we can see where is the position of the. Now come to this picture again. Now say initially the position of the particle is somewhere here. Say, now to see this thing you need to put some photon over there. When photon falls, obviously there will be scattered photon and the recoil electron. So electron moves from this position to somewhere other position. So our first measurement can be represented by, say this is x1. Now again it comes somewhere here. Now the second set of data, when you are measuring, again put some light. You are measuring that this is x2, but again the same thing happens, the electron moves from this position to say any other position somewhere here. Again you are measuring this position, this may be represented by some x3. Take the set of data, this is given as x of n. Now you need to find the average of all this data set. This is basically the uncertainty in that position. So when you are finding the average, a statistical average, this is represented by delta of x. Now you are trying to capture the photon, scattered photon, so we can see what is the position of the particle. So to capture this thing, to capture the scattered light, to capture the light, to see the position of the electrons, we need to use the concept of microscopic resolving power. The resolving power of a microscope is given by R is equal to lambda divided by 2 sine theta. Why this is 2? Because you have the two part of this thing, left side and right side, and the angles are given as theta. But obviously we are talking about the R is equal to x by 2, del x by 2, the half of this portion. So obviously this is x by 2, this is lambda by 2 sine theta. So delta x can be given as lambda divided by sine of theta. So the uncertainty in the position is given by lambda by sine theta. Now we got the position now. Now we need to think about its momentum. Now when you are measuring momentum, again we will going to refer the Compton effect. the light falls, the photon energy falls on electron, there will be scattering and the recoil of electron. So this is the simplest picture of a quantum method. So light, photon falls, electrons, it absorbs some energy, so it recoil in a particular direction, and the scattered photon in a particular direction. Now this is represented by this simple equation. This is the photon momentum, h nu divided by c. Then we can think about it's along this is positive x-axis. Say this angle is alpha and this angle is beta. So one can think about along this side. So this is that along this angle. So this will be the cos of alpha and this is also be cos of beta. Along this particular, obviously this will be the sine component, this will be the sine component, sine of beta and sine of alpha over there. But we are considering along the direction of the scattering. So now we can rewrite the equation. So the in momentum before scattering, so this is given as h nu by c, and momentum after scattering. So momentum after scattering, what happens? The momentum is h nu by c into cos of alpha. This is for the scattered photon, and mv is the momentum of the electron, the recoil electron, along this cos beta direction. So this is the recoil electrons momentum. So after scattering, so this is the effect. Now the momentum is given as along the x direction. This is given as p of x. So p of x is mv cos of beta. So what is mv cos of beta? Obviously you can rewrite this thing. So this will be h nu by c minus h nu by c into cos of alpha. Now the most important part, this alpha is basically, so this scattering portion is moving along this particular direction. Okay, so inside this cone, if it is passing through this, then only this will be observed by the microscope. So there are two possibilities. Either this will be plus of theta or minus of theta. So 90 plus theta and minus theta. Obviously this will give you that nu plus nu dash plus minus nu dash sine of theta. So there is plus value and there is a minus value. So the two extreme values varies from plus 1 to minus 1. So you'll have this plus minus h nu. So plus minus h nu. So you can see h nu by c is the initial photon's momentum, and what is the scattered photon momentum? H nu by c or plus minus sine of theta. Now for the momentum case, we are only considering along x direction. So this is simply given as h by lambda into sine of theta. H by lambda into sine of theta. So h by lambda h nu by c into sine of theta. So this is h divided by lambda sine of theta. Now you have lambda by sine theta for delta x, and for the momentum this is h by lambda into sine theta. So the lambda will be cancelled out and the sine value will obviously cancel out. So you can see that delta x and delta px, when you are multiplying this thing, this gives you a Planck's constant value. So it shows mathematically its position, uncertainty in the position and uncertainty in the momentum. When you are measuring, this is basically mathematically equal to the Planck's constant. So obviously its measurement or its accuracy depends on this Planck's constant value. So when you are measuring momentum, say delta x you are trying to measure, so this must be equal to h divided by delta p of x. So this cannot go beyond this particular value, and same thing is applicable for the momentum. So delta px, when you are talking about delta px, this is equal to h divided by delta of x. And remember the value of h, this is in the order of h is in the order of 10 to the power minus 34. So the measurement or the accuracy varies along with this mathematical relation. So this is the idea of the uncertainty principle. So here we have explained it for the position and momentum. So let me just try it for another aspect, the time and energy. So you know about that relation. So AC is equal to Vt, V into T. In the classical world, in the Newtonian world, we know this one. So this is also valid here. So X here, this is represented by delta S is represented by delta x, is a displacement, is a position. The V, okay, so now we are not talking about uncertainty in velocity, we are talking about uncertainty in time. So we are considering this is delta t. So V is constant we are talking about, we are not measuring V over there. So obviously delta t can be written as delta x by V. Now from this relation we also know the delta x equal to h divided by delta p. So delta t is equal to delta x by v. Again put this value, delta x equal to h divided by delta p multiplied with v. Now we have another relation when particle is moving, so energy of the particle is given as half mv square, or this is p square by 2m. So find the energy uncertainty. So this will be delta E. So actually you can think about, you have the differentiating this one. So delta energy, so E is equal to P square by 2m. So when we are differentiating this one, so this will be delta energy. This is equal to half of m. Okay, so you are differentiating this one. So half of m is there. So you are differentiating, this is V square equal to 2 into V into delta V. So 2 will be adjusted, this is V into m into delta V. So m into delta V is represented by delta of P. So this is given as V is given as delta x by delta t. V can be written as delta x by delta t, and P is there, this is delta V. So now you know, so this is, so you can just delta E is there, so we are taking delta t over there, this side. So delta E, delta t, you got this one. This is equal to delta x, delta p. So you have already got this thing, that delta x, delta p is approximately in a minimum form, this is equal to h, or the Planck's constant, or in a very generalized form, this will be h by 2 pi h cross. So you have got the two cases where you have position and momentum, the uncertainty position and momentum, and uncertainty in energy and time. In both cases the values must depend on Planck's constant, or in a more generalized form, this will be h divided by 2 pi. You cannot break this barrier, it's a physical restriction, it's a natural restriction of the system. Now we will check that what are the applications of uncertainty principle. For that case we are going to try to solve some simple problem in case of atomic world. So a simple question comes, for the non-existence of electrons inside the nucleus, but the nucleons like protons and neutrons, they exist inside the nucleus. Why is this? Now to do this one, so we will try to take, so first we will go to consider the uncertainty in the position. Come to this particular picture. So inside this thing you have a nucleus. So the dimension of the nucleus is very small. It is approximately in the femtometers, again a femtometer. This is in the order of 10 to the power minus 14 minus 15. And the dimension of the atom is in the angstrom order. So you have certain order difference. So now first we are solving it for the nucleus. So the dimension of will be considered as delta x for the nucleus section. Now the delta x is the diameter of the nucleus. This is in the order of 10 to the power minus 14 meter. So its momentum. So you know the uncertainty in the position. So you know the momentum. Now we can calculate this thing. So we have already mentioned this thing, delta x and delta p. This is equal to h divided by 2 pi. So you have delta x, or value of delta x. Put this thing and you can calculate what this should be the uncertainty in the momentum. So it comes somewhere here in the order of 10 to the power minus 21. The momentum is in the minus 21. So the minimum uncertainty of the momentum must be in the order of 10 to the power minus 21. Now see experimentally what we are getting. Now it is observed that when you have the momentum, if you have the relativistic corrections, so first we are considering the relativistic corrections. So energy is given as E square equal to P square C square plus M0 square. So for certain approximation you can write E equal to E square equal to P square C square, or E is equal to P into C. So as this value, the P square C square is quite large, so here just have approximation of this. So E can be given as P into C. For this particular case, the P into C is the energy of the system. So we have already calculated what is the uncertainty in the momentum is in the order of 10 to the power minus 21 and multiplied with that velocity of light. So it gives a energy of 10 mega electron volt. But the problem is, when you have electrons inside the nucleus, the energy must be approximately 10 mega electron volt. It must be. It's a theoretical calculation. But experimentally, it is observed that when the beta particle or the electrons are coming out from the nucleus, the energy of the particle is only 3 to 4 mega electron volt. This is much lesser. Now the concept is, if certain energy or the certain particle having energy which is higher than the binding energy, so it cannot stay over inside this thing, this will come out from this one. So this can be calculated by uncertainty principle. This is the one of the important evidence. Now another way you can calculate, so if you are considering the non-relativistic case for the protons, they are inside this thing, so the momentum is equal to P and the energy is given as P square divided by 2m, m0 the rest mass. The rest mass of the proton is in the order of 10 to the power minus 27 and the momentum uncertainty is in the order of 10 to the power minus 21 for the nucleus zone. So put this value, square this one, divide this thing, and it comes in the order of some kilo electron volt. Now see that energy is in the mega electron volt, but the nucleon energy is in kilo electron volt. It's much lesser, so they must confine within the nucleus. A simple comparison, the electron energy is higher, so as this is higher, it can easily come out from the nucleus. But for the nucleons or the protons, in this case we have considered in case of protons, so the protons energy is much lesser, is in the kilo electron volt, so they cannot overcome this barrier, they must confine in this. So this is one of the important aspects of this thing. Now we are going to check the another case, that energy and the frequency relation. Now we know energy and time, this is given as h cross by 2. So energy is given as h cross by 2 into delta. Say you are having electron, its excited state is in the order of 10 to the power minus 11 seconds. Now we can think about two states, one is the ground state, another is the excited state. Now when the particles are here, when the electrons are there, so it will stay for approximately, so it's represented as tau. So in this case is in the order of 10 to the power minus of 11 seconds. Okay, so the time is known, the uncertainty in the time is known. So delta t is in the order of 10 to the power minus 11. So what will be the energy in this case? So the energy must be given as h divided by delta t or h cross divided by delta t in more accurate calculation. So if you put these values, if you are able to calculate this one, it comes in the order of 10 to the power minus 5 electron. 10 to the power minus 5 electron. Now energy uncertainty is known. So we can easily calculate what is the uncertainty in frequency. Now energy, so E is given as h nu. So you know the energy uncertainty, h is constant, you can calculate what is the uncertainty in the frequency. So it's in the order of 10 to the power 9 Hertz. So what it says, that the frequency in case of transition, so the frequency, so obviously the initially particles are here, you need to supply some energy. Okay, so the particle will move from ground state to excited state, it will stay over there for 10 to the power minus 11 seconds and it will come back after some time. Now again the energy will be released in form of photons. Now the released photon is in the order of 10 to the power 9 Hertz. So accurately you can calculate this thing. So this is the importance of uncertainty principle. So what we have checked, that by using the uncertainty principle, its position and momentum relation and energy and time relation, you can have some idea about the atomic world or the nuclear world. Thank you. We have discussed about uncertainty principle.